Okay. Now we have a second speaker, Dr. Ajanta Goswami, is distinguished academic and research with expertise in remote sensing applications, particularly in glaciology, crystospheric studies, urban heats, islands, landslide, and geohazards. He holds a PhD in geology from IIT Roorkee, Uttarakhand at 2008, and MSc in geology from Guwahati University, Assam, and BSc in geology from Cotton College, Guwahati, Assam. With previous experience as a scientist, engineer, at the Indian Institute of Remote Sensing, IIRS, ISRO, Department of Space, Government of India, Dehradun. Throughout his career, Dr. Goswami has been actively involved in numerous research projects, contributing significantly to advancement in his areas of interest, research and consultancy, projects sponsored by IIRS, ISRO, MOEs and MHRD, DST, IIT, etc. to his accolades. His work include publication in reputed journals, books, alongside active collaboration with national and international researchers. Recognized for his academic excellence, he has received several honors and awards and holds membership in various professional organizations. Dr. Goswami's dedication to the field of geology and remote sensing has established him as a leading expert in addressing critical environmental challenges through innovative and applied research. I welcome you on the behalf of IPS Academy's Civil Engineering Department. Thank you, sir. Kindly enlighten us with your knowledge. Thank you so much.
Thank you so much, Swati. I hope I am audible.
Yes, sir. Yes, sir.
Yeah. Thank you, Devanshi Madam, also for inviting me to this particular program. So let me share my screen first.
So the privilege is all ours.
Thanks a lot, ma'am. So I hope my screen is visible.
Yes, sir.
Okay. So good evening to all of you. I guess it's already late. It's 7:30. So most of you will be tired. However, the topic on which I am planning to talk today is regarding remote sensing for climate change assessment. Specifically, I work on cryospheric hazards in the Himalayas. So I'll be showing few of the case studies that I have done and how else the remote sensing can be used for cryospheric studies. Okay. So I hope you can see me now. Yes. Okay, so the work that I'm going to present in front of you all or discuss in front of you all is not only my work, rather it's a collaborative work with many people, starting with my collaborator, Dr. Anil V. Kulkarni from IIT Bangalore, my student Ashim Sattar, who is now faculty in IIT Bhubaneswar, and there are many other students, like Jaydev, Akansha, Abhilasha, Rohit, who are now working in different departments.
Sir, can you be a bit louder? We can't hear you very clearly. Can you be a bit louder?
Okay, can you hear me?
Yes, sir, no. Yeah.
Okay. So to start with, okay. Yes. So this is what is the global distribution of glaciers, as can be seen from this particular map, which I have taken from this particular references. So what exactly is glacier? Glacier is a moving body of ice, and it moves under the influence of gravity. And those glaciers can be seen either in high latitude or in high altitude. So there are two important things. One is high altitude or high latitude, because in these two places you will find low temperature and where you will find the glaciers. So this is how it looks in a time-lapse image. And there are some more images, like this one is from Everest Base Camp on Khumbu Glacier from 2017 to 2018, where glacier motion could be seen. Again, from 1876 till now, this one is a past and future retreat of glacier in Switzerland, which is according to a medium greenhouse gas emission scenario. And after 2020, massive measures to produce artificial snow are implemented, and it slightly slows melting, but by far does not stop it. So you can see that how exactly climate change has influenced. So the topic is regarding remote sensing and its application for climate change studies. So in that case, cryospheric study is very important because all the glaciers as well as snow cover exist in a very narrow window. So if there is any change in snow or glaciers, so they exactly tell that how climate change has impacted it. So climate change impact can be studied very nicely in case of glaciers. So what exactly is glacial lake outburst flood? So when we talk about glacial lake outburst flood, so it means it's a sudden release of water from a glacial lake, which can disturb river to kilometers and posing a high potential for damage downstream or infrastructure and ecology. And if you look at the last 12 centuries, so earliest glacial lake outburst flood record was documented way back in year 850. Okay, from the sediments and different types of deposits, we could make it out that in last 12 centuries, the earliest record was in the year 850. From that time till 2022, till now, a total of 3,151 globs have been documented across 27 countries worldwide. Okay, so you can make it out that how much this glacial lake outburst flood is frequent all over the globe. If we talk about the Himalayan region, so in Himalayan region till now we have recorded 569 such type of events. So this is one more image which shows us that how glacier mass is being lost, okay, and how it is contributing to the formation of glacial lakes. So whenever the glacier mass is lost, so that particular area where the what is called as the ice has been lost in that particular area, if there is any over deepening site, that over deepening site actually gives rise to formation of glacial lake. So this is one particular map which shows a relation between spatial scale and time scale, and it tells about that how we can study different types of cryospheric domains or cryospheric phenomena, okay, and what type of time scale we can do it and what type of spatial scale you can do it. So you can see that glacier or glacial lake outburst flood or debris flow needs a time scale of about hours to day, okay. And the spatial resolution is from watershed valley level to regional level. At this particular level, we need data to study it. Okay. So total glacial lake outburst flood events, I have already told you that there are a huge number of glacial lake outburst flood events, and around 569 events have been recorded in case of Himalaya till now. And these dots, all the red dots, it indicates that where exactly this glacial lake outburst flood took place in so many years. So let me give a background. So if we talk about hazard, so till now, my other speakers like Amit Anand has also spoken about hazard risk vulnerability. So you all know about hazard risk vulnerability. So if you look at the hazard part, posed by the glacial moraine dam lake, it's different from other hazards. For example, landslide, earthquake, or even avalanche. Okay, because in case of landslides, earthquakes, or avalanches, there are not known or there are certain uncertainties. Okay, could you hear me, all of you? Yeah. So these are involved with not known or there are certain uncertainties. So what type of uncertainties? Where the locations of future avalanche, landslides, earthquakes, and flash floods are not known with certainty. Okay. So we don't know where exactly the avalanche is going to take place. We don't know where exactly landslide is going to take place. We don't know about the earthquakes and we don't know about the flash floods. Although we know that out of hazard zonation, there are certain zones where there is more, which is more hazardous. So there is a probability that in that particular zone, there could be a chance of avalanche or there could be a chance of landslide or there could be a chance of earthquake or flash flood. But with certainty, we don't know where exactly it's going to happen. But on the other hand, if you look at glacial lake outburst flood, we already know the glaciers, okay? And we already know the lakes which are associated with those glaciers. So with great certainty, we know that, okay, if this lake breaches, how much area will be inundated downstreams and how much damage will be created. So we know with certainty that if this lake is going to breach, how much damage it is going to cause downstreams. So we have a certainty in case of glacial lake outburst flood. Apart from that, if there are huge amount of damage which it has caused, if any glove event has caused huge amount of damage, it means our preparedness is not exactly there. We're supposed to be more prepared for that particular type of disaster. So as you have heard about the South Lonak Lake, where there was a huge damage which took place, it was already known that that particular lake is going to breach. And even the mapping was also done, modeling was also done that how much area will be inundated. And still the damage was quite huge. Why? Because our preparedness was not that much. So I'll show you a few more examples in this particular aspect. So the dynamic nature of glacial lake and GLOF is easily monitored by remote sensing and modeling techniques. Okay, so certain images. So to start with, what do you mean by cryosphere? So let me start with what do you mean by cryosphere and how much water is stored in different components of the cryosphere. Okay. So if you look at how much amount of water is stored in different components of the cryosphere and what do you mean by cryosphere? So cryosphere is defined as the portion of the earth where water is in its solid form, either seasonal or annual. And this term came from the fusion of Greek words cryos, which means cold or ice, and sphera, which means ball or globe. And I have referred to one particular book by Barry et al. In 2011, where the term was first introduced where he says that the term was first introduced in 1923 by a Polish scientist, geophysicist, and meteorologist. So the first time this word was used by a Polish scientist way back in 1923. So the word is quite new. And what exactly are there in the component of the cryosphere? So if we talk about cryosphere, it consists of snow cover, glaciers, ice sheets and ice shelves, freshwater ice, sea ice, icebergs, permafrost, and yeah. So if you see the component where exactly the different type of your frozen snows are there. So the first or the major component is in frozen ground, which we call as permafrost or seasonally frozen ground. So 55 million square kilometer in the northern hemisphere is influenced by the permafrost event. Okay, so out of which 22 million square kilometer is due to permafrost. Okay? Second part is snow covered with a maximum cover extent of around 47 million square kilometer in January and mean annual area of around 26 million square kilometers. So snow covered area or cryosphere means all around the world, it is the second major component. First is permafrost, second is snow covered area, and third is sea ice. Okay, so the maximum winter extent of around 14 to 16 million square kilometer in the northern hemisphere and around 17 to 20 million square kilometer in the southern hemisphere. So ice sheet, it holds around 77% of the world's fresh water. So if you look at this particular data, Antarctica, it alone accounts for 90% and Greenland for almost 10%. And the remaining ice caps and glacier consist of around 0.5%. So yeah. So let's look at the geology of the Himalaya. So this is one particular map which I have got from Surly M 2013. This is just a representative map. There are so many other improved maps of Himalaya, the geological map of Himalaya that you can go through. But I think this is good enough for my particular lecture. So if you look at Himalaya, Himalaya is quite unique because it has around 100 peaks which exceed 7,200 meters in elevation. Okay. So in Himalaya, there are more than 100 peaks which are above 7,200 meter in elevation. Okay. The highest peak outside Asia, okay, Aconcagua in the Andes is only 6,961 meters. So that itself tells that how big is Himalaya, how enormous is Himalaya. If we study Himalaya, so you will find that it is actually transboundary problem. So it means it covers 5 countries, Bhutan, India, Nepal, China, and Pakistan. Among them, Bhutan and Nepal are 2 countries which are in Himalaya, which is within Himalaya. If you look at the extent of Himalaya, you will find that the west to northwest to east and southeast arc is around 2,400 kilometers. Okay, this whole arc is around 2,400 kilometers, and western anchor is Nanga Parbat, and eastern is the Namchabar one. If you look at the width of the area, so around 350 kilometers in the west and around 150 kilometers in the east. So that big is the Himalaya. If you look at the formation, that how exactly Himalaya form. So you will find that its formation is a result of continental collusion or orogeny along the convergent boundary between the Indo-Australian plate and the Eurasian plate. And the Arakan-Yoma Highlands in Myanmar and the Andaman and Nicobar Island in the Bay of Bengal were also formed as a result of this particular collision. And this took place in Upper Cretaceous. If you look at the geological age, this particular took place in Upper Cretaceous, which is around 70 million years ago, when the north-moving Indo-Australian plate, which was subsequently broken into the Indian plate and the Australian plate, it was moving at about 15 centimeter, which is around 5.9 inch per year. Okay, at that velocity it was moving, and Indian plate is still moving, but its velocity has gone down. Now it is moving with a velocity of around 67 millimeter per year towards the north. And about out of this 67 millimeter per year movement, 20 millimeter per year of the India-Asia convergence is absorbed by thrusting along the Himalayan southern front. So 20 millimeter each year is adjusted along the thrusting. So because of that, the Himalaya is rising. Okay. And this leads to the Himalaya rising by around 5 millimeter per year, making them geologically active. So you have seen many data, you have seen many papers where it is said that the Himalaya is rising closely at 5 millimeter per year. It's not uniform everywhere, but it is closely 5 millimeter per year, which is because of the 20 millimeter per year of convergence, which is absorbed along the thrusting out of 67 millimeter per year movement of the plates. If you look at the hydrology of Himalaya, so some of the world's major rivers like the Indus, Ganga, and the Sangpo Brahmaputra rise in the vicinity of the Himalayas, and their combined drainage basin is home to some 600 million people. Out of that, 53 million people lives only in Himalayas. So that tells the importance of this particular subject, that how important it is for us to study the Himalayan cryosphere or the glaciers. Okay. So from this prelude, from this understanding that what exactly is cryosphere, why it is important, where, how much amount of water is being stored, okay, then how Himalaya is important for us and what is the characteristics of Himalaya. There are certain research questions that I have actually these are the few research questions I found that any researchers can take it up, which has not been answered completely. Among them is, what is the total snow-covered area in Indian Himalaya? Okay, which should include both permanent snow line as well as seasonal maximum. It means what is the permanent snow line above which you will find snow cover all around the year, and what is the seasonal maxima, that when there is maximum snow covered, how much area is covered. So seasonal maxima is very important because this is a zone which gives rise to the melting. Okay, from there you are getting all the seasonal melt water, as well as avalanches are also triggered mainly in this particular zone, and therefore it is very important to mark the permanent snow line as well as seasonal maxima. The second important research questions which any of the researcher can take up is like, what is the total snow water equivalent seasonally and annually? How much amount of snow water equivalent is there both seasonally and annually? Third important question is snow modeling and discharge estimation or forecasting under changing climatic.
बहुत तकलीफ है सर, बिकॉज क्या है, एक तो दोनों लॉयर की आपस में ईगो, वो बड़ी मुश्किल से उसने भेजा, वो भी गुस्सा करके कि भाई अब तो मैं दाम बढ़ाऊंगा ओंकार।
Yeah, so third important is global runoff modeling and discharge estimation forecasting under changing climatic scenarios.
देखेंगे बाद में।
Then next important question is, what is the status of Himalayan glaciers and glacial lakes and what are the associated dynamics? Okay.
अभी रात को 8:30 बजे उससे मिल रहा हूँ सर, साइड से।
चेतन प्रकाश जी, आपका माइक ओपन है, प्रेजेंटेशन में आवाज आ रही है।
सॉरी एक मिनट, माइक चल रहा है, एक मिनट बात करें।
Yeah. So what is the status of Himalayan glaciers and glacial lakes and what are the associated dynamics? So that is also one of the most important question. There are so many inventories which are already available. Like you can go through the inventory prepared by SAC Ahmedabad. They have an atlas. Okay. They used to prepare atlas every year and they used to show that how many glacial lakes are there, how many glaciers are there, and how it is changing with time. There are certain inventories by GSI also, Geological Survey of India also. They used to do field survey and they prepare those inventories. EC mode has prepared few of the inventory, scattered inventory in few of the regions. RGI, if anyone is anyone know about RGI, okay, Randolph Glacier Inventory. So they used to prepare those inventories for this climate change scenarios. So I was part of RGI and we prepared the version 6.5 at that particular time. So we need to know the status of Himalayan glaciers and glacial lakes and what are the associated dynamics. Then comes glacier mass estimation in basin and regional scale. We also need to know what is the glacier mass balance. Mass balance means how much accumulation has taken place or how much ablation has taken place across one particular year. That we need to know, because if there is positive mass balance, it's good that the glaciers are growing. If there is a negative mass balance, it means it's a concern for us, because in future, if there are any hydropower projects downstream or if there is any water availability downstream, people depends on certain amount of water downstream. We need to know that in future, how much amount of water will be there. We also need to understand the glacier ice thickness mapping and estimation of stored water. So can we map the glacier ice thickness, that how much thick are the glacier ice and how much water is stored on those glacier ice and what is the future? Okay. Mapping the future extent of glacial lakes, both in space and time domain. So if a glacial lake is this much in size, for example, South Lona Glacial Lake, now it is this much in size. In future, how much it is going to grow? Okay. In terms of space, how much it is going to grow and at what time it is going to grow up to that amount. Okay. That also we need to map or model. Then glacial lake outburst flood modeling under different scenarios. So we need to map and model glacial lake outburst flood in different scenarios, all those scenarios that I have talked till now. Final most important thing is standardization of the methods, not freezing the methodology for bringing a commonality. So this point talks about BIS. So Bureau of Indian Standard. So actually we at IIT Roorkee, along with Bureau of Indian Standard, we have started mobilizing one particular movement where we are going to develop certain standards, okay, for all these things, all these work, whatever work has been discussed till now, we are trying to standardize few of the things. This standardization is only in the processes. We are not freezing the methodology, but at least we are going to standardize few things like what type of projection system should be used, okay, how we are going to map, what type of corrections are to be done, and can it be like overlaid on one above another. So all these things we are going to do in future, and we need more people to volunteer in those aspects also. So we have worked on glacier inventory and temporal assessment. So this is one particular inventory that we have developed for Uttarakhand, where we have seen that increase in number of glacial lakes from 1968 to 2016. So you could see there were only 60 glacial lakes in 1968, which has become around 87 by 1994. Then in 1994 to 2001, it became 2102. And by 2016, it was around total 130. Okay. So this is how the glacial lakes have increased with time. How much glacial lakes have increased with time. So you can see from this particular figure. So over 70 new lakes formed in the last 48 years. But if you look at other inventories, so you will find that number of lakes are quite larger in their case compared to our inventory. The reason is the scale of mapping is quite different. Like we have mapped at 1:50,000 scale, and they have mapped at better scale. So I can tell you that how we determine the scale. So scale can be determined as if you know the pixel size. For example, if you are mapping using Landsat data, for example, okay, or any other data, say if you are using 30-meter data. So with 30-meter data, the scale at which we can map is 30 multiplied by 2000, which gives you 1:60,000. So we can map at 1:60,000 if we are using Landsat data or any other data at 60-meter resolution, 30-meter resolution. If you are using list4 data, 5.8 meter. So say 6 meters. So with 6 meters, 6 multiplied by 2000, it means you can map one area at what scale? 1:12,000 scale. So if you are mapping with list4 data at 1:12,000 scale, so you are going to get more number of glaciers. If you are mapping using any data with 30-meter resolution, so you are mapping at 1:60,000 scale, so number of lakes will be quite less. This particular map was developed at 1:50,000 scale, therefore number of lakes are quite less. Again, this is one particular inventory for Arunachal Pradesh. All these reds, okay, red, it indicates the glacial lakes, and you can see that glacial lakes are more conspicuous. Like here in this particular part, it is more conspicuous. Here also you will find most of glacial lake. Here also you will find most of lake. Here the number of lakes are missing. Okay, so by the year 2018, around 1,420 numbers of glacial lakes were mapped for Arunachal Pradesh. Okay. Similarly, this is for Ladakh area. So we have not mapped in this part, we have mapped only in this part. So you could see that in Ladakh area, there were 832 numbers of glacial lakes that we could map, okay, at that particular time. This is for Sikkim. Sikkim has been known for the glacial lakes and which are very vulnerable. Okay, most of the vulnerable lakes are actually seen in Sikkim area. So this is one of the map for Sikkim area for the year 2018, where 240 numbers of glacial lakes were mapped. So most of you who are working on cryosphere or glaciers, you might have gone through the NDMA document where NDMA has recognized 188 different glacial lakes which are vulnerable, and they have said that these are the lakes which we need to target at the initial time, okay, across all different Himalayan states, which is Arunachal, Sikkim, Uttarakhand, Himachal, as well as Ladakh and Kashmir area. So they have mapped 188 different lakes, and every state government is given this assignment to conduct field survey and find out the vulnerability of these lakes and can we actually do risk reduction for these lakes. And there are huge amount of money which has been pumped so that the risk associated with these glacial lakes can be reduced. All the hydropower projects, whichever companies are there, they are directed to do glacial lake outburst flood risk assessment for their dam also, that if there is any such type of event, how it is going to damage or how it is going to impact those dams or reservoirs. Okay. So this is one study that we have done for Mago village in Arunachal Pradesh, which is in Tawang district. Okay, you can see the Latlong. This was one of the lake which was actually recognized by NDMA as one of the most vulnerable lakes in Arunachal Pradesh. And my students also recently, they have gone along with the state government team as well as central team for the field survey. And the total area of Lake 1 and Lake 2 are around 0.85 square kilometer and 0.2 square kilometer respectively. And Lake 1 is moraine bedrock dammed lake. So this is just a flowchart that we have used. So if you see this particular figure, you will find out that how the glacier and glacial lakes have evolved. This is of 1989, and this one is of November 11, 2023. So in 1989, you couldn't see any glacial lake. Okay, glacier area was around 5.84 square kilometer. 1984 also, there was no glacial lake here. Okay. But in the year 2002, you could see there is a formation of glacial lake here. There's a small glacial lake which came up. Here it was not visible, here it was not visible, but here it came up. By the year 2014, this glacial lake has increased in size. Okay, here it was 0.05 square kilometer, here it became 0.35 square kilometer. And by 2018, it became 0.54 square kilometer. And by the year 2023, it became 0.85 square kilometer. So it is growing tremendously. And there is a possibility that in future, if it is breaching, it is going to damage the army installments or infrastructures downstream. Okay, so this is the glacier constantly retreated at an average rate of around 160 square meter annually on average. And the extent of Glacial Lake 1 in the Mago Basin has increased significantly, averaging around 100 square meter within 3 decades. So there is an interesting figure here. You can see that glacier versus lake area I have plotted. Okay, the blue bars shows the glacial area and the red bar shows the lake area, how it has changed. And here I have plotted the curves. Okay, so you can find out that what is the relation between the decrease in glacier area and increase in the lake size. So then we have done, we have used HECRAS as someone was asking that which model is better, like HECRAS or mic models are available and which can be used. So here we have used HECRAS because it is freely available, it is easy to use, and we wanted to see the maximum damage. Okay, we were concerned about the maximum damage so that risk reduction could be done. So for that, HECRAS was quite easy. I'm not going through all this because you all are civil engineers. You know about this thing, okay? How it works, okay? What are the assumptions? There were certain equations that we have used to find out certain parameters. For example, we tried to find out the bathymetric data, like Fujita et al. Empirical model was used, okay, to find out the depth using the area scaling, where area of the glacial lake and DM is depth of lake in meters. So this is what we have find out from Fujita et al. Because Fujita was giving us the extreme event, extreme data. Okay, so we tried to find out the extreme data, that what could be the maximum damage that it can create. Okay, these are some other parameters that we have considered. Okay, so the amount of maximum discharge for lake 1 and for both lake combined are given here. And at different location, if there is 100% breach, what will be the amount of discharge? If 75% breach is taking place, how much amount of discharge will take place? If 50% breach take place, what will the discharge? If 25% breach take place, how much will be the discharge in different locations? So locations are at Lake 1, both at lake at 2 kilometers, at Mago village, which is a village downstream based on which this lake is named. Then settlement 1, which is actually maybe it's an army installment. We are not sure, but yeah, it looks like an army installment. We are not supposed to say that. Then settlement 2 also, and then there is a hydropower project downstream. So how much amount of your amount of maximum discharge can be there in worst case scenario, which is 100% breached, and if 25% breach take place, minimum scenario, how much will be there? Okay. Yeah, so we have then done the hydrodynamic modeling here, and we could see this figure gives us discharge at 2 kilometer, okay, for 100% to 25% scenarios, how our hydrograph looks like. And this is at Mago village, okay, discharge versus time for moraine failure at simulation by HECRAS, so that you can see here. Yeah, for different areas. So this gives us a more a clearer idea. Okay, so you can see at 22.2 kilometers from lake how much area will be inundated. You can see that there is certain amount of settlement here. This whole settlement will be inundated. It will be gone. Okay, it will be gone. If you look at here, so here you can see again there are certain settlement. This settlement is at 37.5 kilometers from lake. This will be also gone. Okay, it will wash out this settlement also. So this settlement is gone. This settlement is also gone. At 41.7 kilometers from the lake, again, you can see certain amount of settlements are there. These will be also gone. It will wash away this thing also. And this is at 43.7 kilometers from lake. And this is the location of hydropower project. So here also you can see how much inundation will take place. Okay. So, and how much time will be taken, it is also given here. So it means these settlements are at high risk. So if we are concerned about, since we already know that this particular lake is quite vulnerable, it is going to, it is growing tremendously, and future it is going to breach. So we need to relocate all these settlements. We need to relocate all the settlement to some certain places, safer places. And these safer places should be such that where it is not affected by any toe cutting also, and it is not affected by any landslide also. So there we need to shift all these base camps. Okay. Then what we have done, we have tried to find out the ice thickness also. Why need to find out the ice thickness? Because that tells about the health of the glacier, that what is the health of the glacier, how thick the ice is, and in future, whether if there is any retreat of this particular glacier, how much the lakes are going to grow. So we have used one particular model, which is called as HICTIM tool, that myself and my collaborator, Professor Anil Kulkarni, we prepared for one HICOM project, for one imprint project. So using that, we have tried to find out the ice thickness. So you can go through different types of ice thickness models. So there is a classic paper by Ferrinotti et al. Of 2017, where he has compared different types of ice thickness models, and he has suggested that which model works better in which scenario. All these models can be classified into 5 groups. One is based on minimization approach, one is based on mass conservation approach, one is based on shear stress based approach, and one is based on velocity based approach, and other approaches also. So this HICTIM model, it works on velocity-based approach. This model works on a velocity-based approach. There is one more model which is quite popular, GLAPTOP 2, which works on shear stress-based approach. Okay. So this is the result of that particular model. You can see that bed elevation, what is the bed elevation of the whole glacier for which we have done the estimation. Okay. So the model resulted with bed topographic glacier thickness and future lake extent can be seen, and it calculated maximum thickness of the glacier was around 251 meters. Okay, the maximum thickness was around 251 meter, and according to projection, the lake will grow this much square meters and maximum depth of around 54 meter. So if this particular lake which is located somewhere here, if it is going to grow, so how much it is going to grow? It is going to grow 2,08,000 square meter and maximum depth of around 54 meters. So that much it is going to grow. So it means if we are planning any infrastructure downstream, so we need to run our model for this value. If we are running for this value, then only it will be futuristic. Okay. If you are running only present day data of the lake as well as its volume, so it is going to give us only present scenario, and maybe our relocation is not going to work after next 10 or 15 years. But if we want our relocation to work after 10 or 15 years or 20 years, then we need to do the modeling based on this particular data, which we have derived from the HICTIM model. Okay. So this is the glacier ice thickness estimation 2023, and the projection of future lake extent in 2023. So you see, this is the present lake, and in future, this lake is growing up to this much. It is going to reach up to this much. Okay. If we consider HICTIM model, and if you want, you can also run other models like GLAPTOP 2 also, and then you can find out how much it is going to. This is basically based on slope break method. So once you get the glacier ice thickness, so you remove the ice, you know the bed topography. Once you know the bed topography, you can simply do the slope break method. You can use the slope break method, and from slope break method, you can find out that how much the lake is going to grow if the glacier is retreating. Okay. So you can see carving of glacier to create a cascading hazard. So these are a few of the carving of glaciers as can be seen in the particular lake. So this is a summary of this particular lake. The lake didn't exist until 1989, and the current size is 0.85 square kilometer in 2023. The glacier is reducing at an average rate of around 160 square meter every year, and the glacial lake area is increasing at a rate of around 100 square meter per year. Okay. The deformation of 39 centimeter in line of sight that can have an impact on the moraine failure to trigger a catastrophic glacial lake outburst flood. Okay. So this is also one thing which we have been targeting, that we try to find out that along the moraine where movement is taking place, where exactly movement is taking place. If there is some amount of movement or significant amount of movement is taking place around the moraine, so we can trigger some alarm that, okay, in future, in this area, some like avalanche may take place, and because of the particular avalanche, the lake may breach in future. Okay. The glacial lake outburst flood model resulted to maximum discharge of around 25,000 square cubic meter per second, and it inundates various settlement area and proposed site of hydroelectric project downstream with a depth of around 111 meters. So at that particular location where hydroelectric power project is there, in that particular area, the maximum that or the water column will be around 111 meter. To examine the further scenarios of Gloff event, a noticeable change in glacial lake expansion is seen, which further over the snout of the glacier with a maximum depth of 54 meters. So this is a futuristic scenario of that particular lake. So now let me take to, this is one example from Mago village. Let me now take to the other example, which is, I think you all have heard about one example from Uttarakhand, which is in Rainy village, where due to one avalanche, this huge amount of destructions took place in two hydropower projects downstream, killing more than 250 people who were working at that particular moment. And why this is unique? Because this event took place in winter. Generally, glacial lake outburst floods are expected during summer when there is more melting and water is more in that particular area. But this event in Rainy Village took place in winter. Okay. So at that time, the only data which was available was the your discharge data, which was downstream, as well as there was one AWS also. It was located in Topo 1. So there are certain images which were available at that time from Planet Lab. As you look at these images, you would see that on 7th of February at around 10:33 a.m., you could see that certain amount of dust, okay, could be seen in this particular area. And by 10:58 a.m., the dust was gone. Okay, it settled down. So it took approximately 20 minutes for the dust and ice to settle to the ground. There's a very good paper in the journal Landslide by one of my students, Priyom Roy and Tapas Martha, where they have done one study, this particular study, where they have shown how the remote sensing data can be used for time freezing, how it can be used for time freezing, and how you can find out that when exactly the avalanche triggered. Okay, what was the time when the avalanche triggered and how much time it took for the avalanche to settle down? Okay, the whole movement to settle down. So this is one of the data which shows that it took 20 minutes for the dust and ice to settle to the ground. Okay, so these are some more images. Like in 6th of February, you couldn't see anything. On 7th of February, you could see that there is some amount of movement. Okay, those huge avalanche took place. 8th of February, you could see that there is one whole open area which was created, or whole vacuum which was created here. Yeah, this is more close up of that particular area. Okay, so we did a detailed study of that area. We did a Reiki along with the NDMA team, and we can see that there was a glacierate which was marked by the Survey of India, which was marked in Survey of India topo sheet also. So there is a glacierate, okay? And this one actually dislocated and which created the whole damage. So this is the path along which the material moved. So initially we thought that whether it is due to any what is called as avalanche, glacial lake outburst flood or not. But the lake which was on the upstream, it was intact. There was no movement here. So whatever movement could be seen is from only this zone. So the avalanche took place from here, and this is the confluence point, and from there it started moving downstream. Okay, this is, you can see the eroded surfaces also. And this is more close up. So even the DGRE, they marked that there are some other area also where future avalanches can take place. So like this one is one of the area where future avalanches can take place. Okay, this is how the movement. Okay. So there were certain questions that whether that particular avalanche has created so much of water as well as debris to move down, means how a huge chunk of ice melted so fast. So there are different types of theories. Among them, there is one classic point which is given is that in that particular valley, you will see there are many sags, and these sags are filled with water. So there was already lots of water saturation in that whole valley area. So when this avalanche took place, what it did, the impact was like squeezing out. It's tried to squeeze it out like tomato. Okay, so when you press it, so it squeezed up, and the all water as well as the material tries to flow down. So based on that, this movement took place. Okay, which I have given here in this equation. I have tried to prove that how rain on snow triggers the melting. Similarly, if there is already melt water available somewhere, how it is going to trigger more melting in that particular area. So there are some file photographs of the damages that took place in that particular area. After this movement, after this avalanche, due to this huge amount of debris which moved down, a small lake formed here. This is a small lake which formed here. And there was a concern that if this lake breaches, it is going to create more catastrophe downstream. So there was a team of NDMA where we went there to find out that what is the scenario in the ground, and if it breaches, how much amount of damage it is going to create. So all these are some file photographs. Okay. So these are few of the parameters. Like length of lake was around 300 meter, width was around 50 meter, height 60 meter, surface area 2,500 square meter, volume around 8.5 lakh per meter cube. Okay. So these are few of the figures that could be seen here. Like distance of Rainy Village from the lake is around 5.26 kilometers. Distance of Topovan Dam from the lake is around 13.32 kilometers. Maximum water debris flow height along the flow path is around 40 to 45 meters at few locations. Average maximum flow height over the complete path could be around 6.87 meters. Maximum flow velocity along the flow path could be around 34 meter per second. Average maximum flow velocity over the complete path could be around 14.16 meter per second. Average maximum maximum flow velocity. These figures, why it is important, why I'm showing all these figures, because I'm going to compare three events. This is one event, then I'm going to compare it with the Kedarnath event, and there is one more event which took place way back in 1894, which is called as the Gohnatal incident. So I'm going to compare this, therefore I'm showing you all these figures. So let's go to the Kedarnath disaster now. So we have studied one disaster, which is the Rainy Village incident, which was because of avalanche. Now let's go to the Kedarnath disaster. Okay. So in 2013, this is one particular area which is called as Rambada. If anyone has gone to Kedarnath before 2013, they might have remembered that there was one place which is called as Rambada, midway between Kedarnath as well as the Gaurikund, that area. People used to take rest in this area, and there were a lot many small hotels or places to stay, and around 5 to 10,000 people can stay here. Okay, during day or night, and around 5 to 10,000 people used to stay here. So after the disaster, this whole area was gone. Nothing was visible here. As you can see in this picture, nothing was visible. So it means this whole event destroyed this whole area, and around 5 to 10,000 people who were locked here at the time were gone. Okay, this was the scenario with the Kedarnath temple at that time. The plinth area, okay, the floor area at that time was around 10 feet, okay, above ground level. But after the disaster, the ground was completely, it was filled with debris from that glacial lake, and the debris came up to the level of the floor area of this temple. Okay, so as you can see, this was the first image which was available at that time for the rescue operation. At that time, I was working with ISRO, and we were asked by different agencies, Indian Army as well as Air Force. They wanted to know that how exactly this area look like now, and whether if they are going for any rescue operation, what could be this possible path through which they can travel there. So we used LIS4 images as well as we used Cartosat DEM, and we tried to find out how much area is damaged at that time. So it was the image at that particular time that we have supplied to Indian Army as well as Indian Air Force. It was a collaborative work between us. Okay, so you can see how much damage took place at that time. So this is a lake. This lake picture I have taken from internet. So before the breach, it looks to be a very small lake, and it was around 3.4 to 3.6 hectares with length of around 320 meters and width of around 160 meters. Now you see, after the disaster, it's me as well as my friend Praveen Thakur. Both of us are standing here. You can see that how much amount of sedimentation was there and what was the size of the lake. Okay, before image and after image. Okay, there were many helicopter crashes also, and we tried to find out the locations also where exactly those helicopter crashes took place, and if there is someone to be rescued, how exactly they can move there. And these are the scenarios at that time. This is one of our PhD scholar. This is the bridge. Okay, at that time, you can see this bridge. Now the whole area was eroded at that time. It's me, and it was quite common. So this is the file photograph after the disaster, and this is a file photograph from GSI 1882. Okay, so why this took place, we all know already. I'm not going to go in depth, but yeah, Dehradun received record amount of rainfall, around 595 millimeter of rainfall in 48 hours. And it was because of a combination of two different activities or active systems, namely westerlies as well as southwest monsoon, because of which huge amount of rainfall took place in very less amount of time. Uttarakhand were affected. If you look at the size, the Chorabade Tal, which is located only 2 kilometers upstream of Kedarnath temple, so the bridge length as well as width is around 62 to 64 meter. Okay, it was V-shaped in session, and it was around 62 to 64 meters as we went to the field and we measured. Water level in the lake had risen approximately 20 meters. Lake area before breach was around 3.4 to 3.6 hectares with a length of 320 meter and width of 160 meters. Total volume of water is estimated to be 7.1 multiplied by 10 to the power 5 meter cube at that time. Okay, so this is the location of DGPS survey, and the peak discharge that, okay, so the average discharge was estimated to be around 1,192 meter cube per second, considering the fact that the lake emptied in 5 to 10 meters. Where we got this data, 5 to 10 meters, actually we interviewed few of the priests who were present at that time and who survived. So they told us that within 5 to 10 minutes, everything was done. Okay, all the damage was done. So with that figure, we tried to find out the average discharge. It could be only 1,192 meter cube per second only. Okay, with this estimation. The peak discharge is estimated as 5,376 meter cube per second by using the dam break formula given by Hunger et al. And referred by Rickenmann. So this is the equation that we have used. Okay, this is the your V-shaped what is called as insertion. You can see the insertion. This is the student for scale. You can see that how deep the insertion was. It was 62 to 64 meter. Okay, in V shape. Considering the valley width at Kedarnath town around 320 meters, average water column height is estimated to be around 3.7 meter for a duration of 10 minutes. It means for 10 minutes in the Kedarnath township, the water column height was around 3.7 meters. So 3.7 meters means it is more than around 11 or 12 feet. Okay. So if it is more than 10, 11 feet, it means look at the height of human. Okay. Normal height of a human being is around 5.5 meter to 6 meters. So it means for 10 minutes, if someone is below water, what will happen? And that's why so many people died. So this particular incidence of Kedarnath can be compared with a very old incidence, which is also called as Gohnatal. Okay, Gohnatal incidents. So this Gohnatal incidents took place in 1894. This is again a file photograph. Okay, sorry. Yeah, so devastation of 2013 and 2021 can only be compared to Gohnatal Lake Bridge flooding in 1894, where you can see this is the lake deposit. This whole area is lake deposit. So here a lake was there, and now since the lake is not there, so you can see the lake was strand deposit. So it was a spectacular lake which was created when a huge rock fall from the right bank of Birahi Ganga River, a tributary of Alaknanda River, blocked the river in September 1893. The first breach took place in 25 August 1894, causing widespread inundation in the downstream. Okay, so how damming took place? Damming took place because there was a landslide which took place on the right bank of Birahi Ganga, and the side of a steep hill measuring 1,300 meters above the level of the stream crushed down into the valley, bringing large blocks of limestone that formed a dam of more than 3 kilometers wide at the base and 600 meters at the top. And height of the lake was 270 meters, and the total volume was estimated to be around 150 to 200 million meter cube. Okay, so if you see this picture, so this is the scar of that landslide. From here, the landslide took place, and this is landslide deposit. Okay, this is a paleo landslide deposit, and this is where the lake was formed at that time. So Gohnatal in 1894. After this landslide, this is the huge landslide, and Gohnatal in 2006. Okay. So in December 1893, the area of the lake was about 2.5 square kilometer, and its depth was around 145 meter. In Kedarnath, it was hardly 20 meters, but here it was 145 meters. Lake length was around 320 meters in Kedarnath. Here it is 2.5 square kilometer lake area. By July 1894, the lake had become nearly 6 kilometers long and 800 meters broad, and the level of water had risen nearly 55 meters to a total of 200 meters. Just imagine how big lake it formed. Okay. The first breach which took place was at 11:30 hours on 25 August 1894, and the lake volume at that time was around 470 million meter cube before the first breach on 25 August 1894. So, which was followed during that breach, 283 million meter cube of water was released. But in case of Kedarnath, only 0.7 million meter cube. Okay, here it is 283 million meter cube of water was released, and 187 million meter cube was left. Still it was left, which was partly released, and lake was filled up with sediments in subsequent 78 years. So during August 1894, the drawdown from the lake was 119 meter, which happened over a period of 4.5 hours, equivalent to average discharge of 17,479. So if you look at Kedarnath, it was around 1,900 meter cube per second. Here it was 17,479 meter cube per second. Okay. But at that time, Britishers were there. They did very nice work. What they did, they marked the anticipated flood level was marked by masonry pillars, which was installed at every half a mile along Birahi and Alaknanda Valley at a height of 60 meters above the ordinary flood level. 8 suspension bridges were removed at that time. The pilgrimage road to Badrinath Shrine was diverted to minimize the impact of disaster. There was a British soldier, Lieutenant Cruikshank, who was positioned with telegraph cable at that time. So at that time, telegraph cable was very innovative, or it was quite new technology and very costly technology. But Britishers, they used the best technology available at that time, and they laid a telegraph cable up to that particular lake, and they put one British soldier, Lieutenant Cruikshank, who was positioned there to watch the lake, and if there is anything, he is going to inform downstream. So the first sign of breach was heralded by the sound of bell. There was warning was communicated by telegraphic messages, bonfires, rockets, beating of drum, all these things were done. So for the first time in Garhwal, Himalaya, the telegraphic connection was established and used for emergency communication. Okay. So the flood water hit Srinagar. This is not the Jammu and Kashmir Srinagar. This is the Srinagar in Uttarakhand. So it hit Srinagar 116 kilometers away in 4 hours with a speed of around 8 meters per second. And Srinagar, with a population of 2,000 in those days, was completely destroyed, although none of the people died. Okay, none of the people died. They were already evacuated. However, the infrastructure was lost, like the Palace of the King, police station, Dag Bungalow, tourist rest house, all these were completely destroyed. So these are different flood levels. Like in Chamoli, it was 49 meter, Rudraprayag 43 meter, Karnaprayag 40 meter, Nanprayag 34 meter, Srinagar 13 meter, Haridwar 3 meter. At that time, the total amount of damage which took place costed around 95,000 rupees. So if you add inflation, so you will find that it is so many crores of rupees which was lost during that time. No life loss was reported except 5 persons who insisted on remaining just below the dam. Since they said that we are not going to move, so they only died. So as I said, the first breach took place in 25 August 1894. Second breach took place in 1924. The third major breach occurred in 1970, which coincides with the Great Alaknanda flood, which is also called as Belakuchi tragedy of 1970. And due to the heavy and continuous precipitation for several days prior to 20 July 1970, Gona Lake again rose and breached for the third and final time in 1970. Okay. So here is a comparison between all these events. If you look at the rainy village event, you will see the volume in million meter cube is around 0.85, length 300 meters, width 50 meter, depth 60 meter, average discharge 3013. This is estimated. Okay, this one is estimated. Chorabari Tal volume was 0.7 only. Okay, 7 million meter, 0.7 million meter cube, length 320 meter, width 160 meter, depth 20 meter, total 1192. Gohna Tal was around 470 million meter cube. So compared to this, see how many times it is bigger. Length 6 kilometers, width 800 meters, depth 200 meters. Average discharge was 17,479. Quite huge. No comparison to Gohna Tal incidents if we compare Rainy Village as well as Chorabari Tal. Okay. Similarly, we have worked for South Lonak Lake also. So this is one of the work of my PhD scholar. So when we tried to find out the risk of South Lonak Lake, so these are a few of the bathymetric data which was already available. And we can find out the size of the lake as well as if it is going to grow, how much it is going to grow. And we try to find out how much water is already available there. There were different scenarios that we have used, scenario 1, 2, 3, 4. So this paper has been reported a lot during the South Lonak Lake incidents, where people said that like whatever we spoken at that time actually happened. The same scenario actually happened. Okay. So these are few of the results of that particular study. Yeah. So I'm skipping it. Similarly, we did a study for one more lake, which is in Uttarakhand. And this particular lake is along the, what is called as the Satupant Lake. Okay, it is along Alaknanda Valley. So if you go beyond Badrinath, you will find Satupant Lake is there. So when this Kedarnath Lake breached, there were so many newspaper reports where people were saying that Satupant Lake is also growing. If it breaches, it is going to destroy, according to the newspaper report, is going to destroy the Badrinath shrine, as well as it is going to come down. And there is a JP power project, which is also going to be destroyed. So we tried to do modeling for that lake also. So we did the modeling for that particular lake also. These are file photographs, how the JP dam was completely destroyed and how much time the water will take to reach Mana village. Okay. Then 10 kilometer downstream, then 6 kilometer downstream, and Glof at just the Satupant Tal. So this is at Satupant Tal. This is 6 kilometer downstream. This is 10 kilometer downstream, and this is at Mana village. And how much water discharge will be there? Okay. How much time that water will take to reach the dam site? So peak flood 44 minutes after the lake failure event. So it will reach the dam sites. Okay. So these are a few of the available informations that we can model. So what will be the water velocity? So you can see the scale. It gives that how much velocity will be there. So towards red, it indicates more water velocity. So it's around 18 meter per second. And this gives you the water depth information, how much water depth will be there. Okay. And this is the particle tracking. Yeah. Yeah. So these are few of the studies that we have done for different parts of Uttarakhand. Apart from that, we have been doing many other consultancy works also for different hydropower projects where we have tried to find out the risk assessment. Okay, if the lake breaches, that how much risk is there, because of the new development with the government of India. They have suggested that it should be done. It's mandatory for all the hydropower projects to do it. So we have been doing it. And there is tremendous scope. See, there are 188 different types of lakes, which has been identified by NDMA in first report. So first 188 lakes are to be studied. Okay, and the risk assessment should be done. Not only present risk assessment, but also the future risk assessment should be done. Okay, which is the requirement. So it means we need lot many research scholars and lot many people, lot many researchers all around India who need to focus on those glacial lakes. And in future also, there are more number of glacial lakes which will be categorized as vulnerable. Okay, so in next report, I think it will the number of lakes will increase. This is the first report. In future report, the number of lakes will increase. So we will need more people to focus on those lakes and study in detail. So this is just one example that I have tried to show you. Similarly, what we have done that whenever we are doing cryospheric study, there is one problem which is mapping the snow-covered area. So the most popular among them is NDSI. You have heard about NDSI, which is used in optical remote sensing, normalized difference snow index, using which you can actually map the snow-covered area. However, NDSI has got one problem, that when we use NDSI, then water and snow cannot be separated, because the reflectance of water and snow in sphere as well as the visible band is almost your ratio is same. Okay, intensity may be different, but the ratio is same. So when we take the ratio, okay, when we normalize it, the ultimate value becomes almost similar, and therefore we cannot distinguish. Therefore, we tried to develop a new model, which is called as SWI, which is an improved snow cover mapping model, and which we have published, and you can use this also. So snow is highly reflected in the visible region of electromagnetic spectrum, making it possible to easily distinguish from satellite image from other land features. So these are the equations, like NDSI uses green minus square by green plus square, and NDSII, which is proposed by Zhao et al. 2001, it uses red and square band. Okay, but all this model has got one or other problem. So limitation of NDSI is that we cannot actually distinguish between water as well as snow. Both are water bodies generally shows low reflectance, but its NDSI value is quite high. Because of higher NDSI value, it is always misunderstood as snow. So we developed this model where we have introduced NIR. Okay, if anyone has studied the spectroscopic property of water, so there's a different set of lecture on spectroscopic property of water, you will find that water has a subtle, okay, your reflectance value in NIR goes down. Okay, for water, very subtly it goes down. So if we are using NIR, so there is a spectral separation. There is spectral separation between the snow as well as water in terms of its reflectance, and therefore it helps us to actually separate these two bodies. So in SWI, we have introduced, apart from green and square, we have used and introduced NIR. And when we use NIR, so we could actually separate between water and snow-covered area. So these are a few of the examples that I have shown here using Landsat 8 data. Okay. Then AWIPS data also we have used here. And we have also used spectroscopic data also, okay, field spectra also to find out. So these are a few of the examples. These are the field spectra using which we have tried to find out the differences. So why I'm showing it here, that if you are using, if you are working on cryosphere, you can use this particular index also, and I am sure that you are going to get good result. And if someone want to improve it in future, you can work on this algorithm and you can improve it also, because at present the problem is whenever you are using optical data, the problem is to differentiate between snow covered area as well as water body. Using SWI, where we have used NIR band, we can actually do a good job, but I don't know about the exact benefit in future. So this was one more work that we have done here. So what we have done here is there was one question. Question was, can we find out the maximum snow extent? How much snow extent is there, maximum snow covered area as well as permanent snow covered area. So to get the maximum snow covered area as well as permanent snow covered area, you need to map that thing. And for mapping, the problem is whenever you are using optical remote sensing data, it is always having a problem of cloud. If there is cloud, So cloud shows non-selective scattering. So since it shows non-selective scattering, so that area will be masked as white color. So since it is masked white color, you won't get any information that what is lying beneath. So here, as one of our output, we have worked on the Indus Basin. So we have used MODIS, Aqua as well as Terra data. And using these two data, what we have done, this is the algorithm. So there are actually 6 steps. The first step is merge Terra and Aqua data. Second is temporal filtering. Third is the elevation filter. Fourth is spatial filter. Fifth is spatial plus elevation filter. And last is cloud masking. So when we merged Aqua and Terra, we could see that merging data in step 1, it has reduced cloud cover. Okay, now it became like it was 24.5. Here it was 13%. It has gone to 10.1%. Okay, so using these 6 temporal windows, okay, 6 different temporal windows, we can reduce the step 2. In step 2, what we have done here is, step 2 is about the temporal filtering. So in step 2, using temporal filtering, 7% cloud was only there. Okay. Step 3, it was left up to 6.8%. Step 4, 6.6%. Okay. Step 5, 4.7%. And finally, it was around 0% cloud. We have shown one image where it is 0% cloud because it is based on certain assumptions also. Okay, there are certain assumptions which you have shown here. You can go through our paper also. You will get to know our assumptions, and all the assumptions are shown here. And I can share the slides also with you. Okay. So that's how we got snow cover data. Okay, like in different steps, how we have removed the cloud cover. So now we are getting more snow covered area. So we can map, and this plugin is also available in GitHub. You can download this plugin and you can use it. Okay. So using this, what we have done, we have tried to find out the snow-covered area in Himalaya. And how we have tried to find out the snow-covered area in Himalaya, we have used snow persistence as a proxy. So what is snow persistence? Like if we have 48 images for one particular year. So because MODI's, your 8-day composite data are available. So when we are using MODI's 8-day composite data, so it means for 48 images are available for 1 year. So in this 48 images, if one pixel shows snow covered in every 48 data after the cloud removal, it means that is permanent snow covered area. Okay. And if any pixel is showing less number of snow covered data, it's seasonal snow covered data, like 50%, 20%, 10%. So like that, you can find out what is permanent snow line and you can find out seasonal snow line. Although our model, it worked at only 1 kilometer resolution, spatial resolution. So it is poor one. So the fractional snow covered, we have not worked on. So if anyone can develop it for Landsat data, so it means you will get a more detailed data. Okay. The detailed information will be there. So that's how we try to find out the permanent snow covered area as well as seasonal snow covered area. So these are few of the work that we have done, and these papers are available online, or you can write to me and you can go through those papers. So we are open to collaborations with all of you because I know most of you are faculty and you all have lots of good idea, or you all are working on different aspects. So we can work in future in these aspects that I have shown. For research scholar, definitely I can say that the research questions that I have noted down here, you can definitely go through these research questions. And if you want to work on cryosphere or Indian Himalaya, you can work on any of this research question. Okay. And if you find any more interesting questions, you can share with us also, like what more is supposed to be done in Indian Himalaya. So with that, I thank you all for listening to my lecture as well as for your patience. So thanks a lot.
Biosphere. Thank you so much, sir. I would like to open the session for any questions or doubts if the participants have or would like to interact with sir. Sir, indeed, your talk was very fascinating, and the aspects which you discussed over here are very aspiring to us. Thank you so much, sir, for taking out of your time out of your busy schedule, and you accepted our request for enlightening us today.
Thank you so much, ma'am. Thanks for the opportunity.
Thank
I
you,
think
sir.
there is
Thank you.
Rajeshri Kamath, she has raised hand.
Yes,
Yes.
in fact, I just want to appreciate the work. In fact, I am also one of the nodal officers of NIDM, and recently they had launched project proposals with respect to glacial this thing GLOF. So I hope I was like this work seemed just impossible. Last year only I had been to Ladakh and all those areas of Kargil and all. So just amazing work. That's all I can say.
Thank you so much, Rajeshri ma'am.
We will shortly inspire our students to go into this field, and this will require a lot of training and preliminary studies, and the site, going to the site, and a lot of work beforehand also to understand the basics also.
Yeah, thank you so much. Yeah, you are right that NDMA has recently, they have actually launched a mega project where they have given huge amount of money to all the state governments to conduct glacial lake outburst flood study as well as vulnerability assessment. And all the state governments, they are working with other nodal agencies also, like they are working with NCPOR, they are working with different IITs also to do those studies. So any one of you, whoever is interested, they can participate with those state government agencies and they can target few of the lakes. So you can work on few of the lakes. There are some more openings coming up. Like recently, I have heard that MOES is going to float some more projects on glacial lake outburst flood studies or cryospheric hazards. So these are some good opportunity which any of our faculty as well as not research scholars, but at least faculty can target. So if they are working on some niche area, they are looking for some niche area or some solutions. If you have any solution, so you all can submit those projects in MOES also. ISRO is also funding a lot in this aspect, so they can work with ISRO also. There are possibility of collaborating also, like there is a DST pair proposal is there, and there are some other proposal where we all can collaborate together, and like 2-3 institute can come up, and then we can submit some proposal, which will be more meaningful, and that is going to help us all because we are going to give some good solution if possible in that way. Yes, thank you, ma'am.
Thank you so much, sir. Thank you, sir. Looking forward to some more works or some opportunities. If even if I'm able to contribute something, then we'll reach out to you, or you can also reach out to us. Thank you, sir. Thank you so much.
Ma'am. Thank you.
Thank you so much, sir. Definitely looking out for opportunities in which we can work collaboratively in future.
Thanks, ma'am.
Thank you so much for your
sir.
support, sir.
Thank you, sir.
Thank you.
Have a good day.
Yeah, thank you. So I'm signing off. Thanks a lot.
Okay.
So participants, we are at the end of the day 3 for this FDP. Looking forward to seeing you tomorrow again at 6 p.m. in the evening, and hoping an active participation from your side as it has been from the day 1. Thank you.
Thank you so much, ma'am.
Lovely sessions, ma'am. Thank you.